the webinar. What I'm basically going to do as we start off here is we're going to talk, a little bit about mechanism dynamics and also behavioral modeling. Just have a very quick PowerPoint of some of the things you can do with both of those extensions in Creo, and then we'll then go into a demo. And the majority of this session is going to be a hands-on demo where I show the tools in both extensions. Now at this time, before I continue along, I want to pause here for a second and interject a couple of polls, just so that way I can gauge the temperature of the audience and your interest in this. And so I'm going to pull up a poll on the screen here, and basically what I want you to do is just pick which one applies to you. First off is for you to describe your interest in mechanism dynamics. And so is it a case where you're currently using it and you want to learn more about mechanism dynamics, or is it a case where you know what it is, you wish you had it but you currently don't, or you don't even know what mechanism dynamics option is or what it does. So I just want to pick one of those bullets in there, and then we'll go ahead and continue along. Okay. We have a majority of people voted, but we're still waiting on a couple more people here. Okay, so we'll close the polls right now, and this is actually interesting. Basically, if I share this, about half of the people are aware of mechanism dynamics. Some currently use it, and others, wish they were using it, but currently are not. And then about half of the people don't even know what mechanism dynamics option is or does, which I wouldn't have expected that. But yeah, I guess that's exactly why we're here in this webinar. And so I'm going to go ahead and go through some examples and use cases of that. Next poll question, just really quickly, is to describe your interest in behavioral modeling. Let me launch that as well. Yeah, so describe your interest in behavioral modeling. And again, similar options as before. Do you currently use it, and you know about it, or you don't even know what it does, or you've heard about it and you wish you guys have it, but you currently don't. Okay, we're just waiting on a couple more people here to vote in before we close the polls. A few more seconds. Okay, so we'll go ahead and close that poll here. And if I share the results of that, this is actually flipped the other way around. There's an overwhelming majority that currently use it, and they want to learn more about it and what it does. And there's some people that don't even know what it does. And so what I will say for everyone that's trying to learn more about behavioral modeling, at the bottom of the GoToMeeting panel, there's a questions section there, or there's also a chat section, depending on which one you prefer. I want you to type in your questions in there. So if you have specific questions about behavioral modeling, about how to do specific things or how to use it to achieve a particular kind of result, if you have specific questions about behavioral modeling, please type those in there. Either at the end of this webinar, I'll take a look at some of those questions, and whichever ones you can answer on air, we'll do that. And if not, you can go ahead and, I'll send you an email or follow up with you after the webinar. And we could potentially use that as a gauge to potentially schedule another webinar in the future where we address those questions, in more detail. So if you have any questions, about, using more of behavioral modeling, please type those down in the questions box, and we'll make sure we get to them. Okay. Let's see. Okay, so we'll go ahead and continue along with this, and we'll just do a quick introduction here with Audrey Systems. So we are a product development consulting firm, and we've been doing this now for many years, and we primarily specialize in CAD design, CAD data management, and also simulation products as well. And so whenever it comes to generating the concept or the idea, building that, and then also simulating the performance, and also the data management side of things, where you're managing that CAD data, we've been there and we've done that with with a lot of our customers. And this is just a small smattering of some of those. Next up in here is what's it called? Again, just the last brag slide before we get to the actual content. We've been rated what's it called? One of the top 5,000 fastest growing companies, for 4 consecutive years, and also in Northeast Ohio, we've been on the Weatherhead 100 list of fastest growing businesses in Northeast Ohio for the last 3 years consecutively. And so when it comes to what we do and being able to help our customers achieve higher levels of success, we're definitely very, very well versed at being able to do that, and that's reflected in our accolades as well. Okay, now quick introduction here with mechanism dynamics. So in Creo, whenever you get the base seed of Creo, and you click on the applications and the mechanism tab when you're in an assembly, that typically will take you into the mechanism extension. And the base mechanism extension is really only a kinematic analysis module. And so that will only allow you to define your mechanism with the different joints between them. And you can define servo motors that basically either move linearly at a say a linear rate per second, or an RPM, for example, rotations per minute. And you can analyze the kinematic behavior of your mechanism, how fast particular areas of your mechanism are moving, what the position, velocity, or acceleration of those parts of your mechanism are. Those are the kinds of things you can do with the base mechanism module. Now, an additional module is available, which is called the mechanism dynamics option. And what that adds to it is not only just the positional or the kinematic aspect of things, but it also adds in there the consideration of forces. And so if you think of anything in a mechanism that requires forces, the mechanism dynamics option will add to that. So for example, you can consider inputting user input forces or torques in a mechanism dynamics option model. You can consider the effect of gravity on the weight of all your different components based on their geometric size and the materials they're made out of. You can also consider the effect of having springs in your system that have a certain stiffness, and then that inputs a force, and also having motors that input a particular torque on your system as well. And then the resulting output variables that you additionally get are also going to be force-based as well. So you can get, for example, the reaction force at certain connections or constraints. And so that's basically, mechanism dynamics. Now, now again, so some of the benefits of this here, are, you can design, much lighter and stronger mechanisms very quickly, and very easily reduce your development time, because instead of building something only to see that it doesn't work, you can test it virtually on a computer and optimize performance before building an actual physical prototype. Another very valuable another very valuable benefit, and we're going to go through an example of this, is you can use it to size your motors and springs and dampers. And so that way, if you know that you want a particular performance from any of those components, you can size it to determine what the minimum amount of motor speed or motor power or spring stiffness you need to give you your required performance. Okay. Now with behavioral modeling, this is again, I guess, a slightly different ball game. For those of you that are not aware of behavioral modeling, it primarily you use it to design for product performance. And so BMX is a case where you understand some sort of qualitative metric or performance that your product has to have, and then you can translate that into quantitative values or data that you can input into Creo and have Creo optimized for. So a quick example of that is a customer that we had where they make rotating cutting heads that spin about 3,000 rounds per minute, and then they cut grooves. And whenever they typically manufacture their heads, they have to spend lots of money in a post-processing facility balancing those heads. And so they wanted to ask us, what if we could design those heads in Creo and they come out balanced already? Then we don't have to spend as much of the dollars on the post-processing and balancing it. And so we came out and said, okay, well, you can use BMX for that, and what you want to do is minimize the distance between the center of gravity and your axis of revolution. If you do that, you minimize the wobble, and when you minimize the wobble, you achieve your performance. And so they were able to build in that feature into their model to where Creo will automatically change certain dimensions in order to minimize that distance between the center of gravity and the axis. And that way they went ahead and produced much better models out of their manufacturing line, even before they were ever taken to a post-processing facility to be balanced. And so that's basically what behavioral modeling enables you to do. And as a result, you're able to dramatically reduce your development time, because it gets you the best possible solution within your design space very quickly. And not only that, but you can also tweak certain dimensions and understand your model sensitivity to certain dimensions. And so you can get an idea of if I change dimension A, how does that affect parameter number 1 that I'm interested in? Or if I change B, how does that affect parameter number 1? And do they both affect it the same, or does one have a much bigger influence on it than the other? Those kinds of questions where typically as a design engineer, you would just, make a wild guess for dimension value, type it in, and, wait to see what happens. In this case, behavioral modeling can automate that process and intelligently reach an optimized solution if that's what you seek in this case. And so I'll pause here for now and switch over to what's it called, Creo, where I'm going to show some demo examples, and these are going to be wide and varied. Some of them are going to have purely mechanism dynamics components in there. Some of them are going to have a combination of both, and some are just going to have some BMX features in there. But once again, for all of you that have more questions about BMX and what to use it for, if you could type those questions in your in the questions box at the bottom there. So if you have questions about, well, how do I use this feature, or I see this button in the BMX tab and I don't know what it does, can you explain that to me? Go ahead and type those in there, and I'll get to those at the end of this webinar here. So I will see here, switch my screens. Okay. Okay, so First example is right here. This is primarily just a mechanism dynamics model, and what we have is a trunk box. And almost anyone that has had a car and you've opened either your trunk or your hood, depending on how either one was designed, almost anyone on this webinar that's done that has interfaced with a similar, mechanism like this. This is basically intended to be a hydraulic cylinder that inputs a force. And if I just open and close this, that's exactly what the lid does. So it, closes and opens like that, right? Now we're in the very early stages of designing this, and one of the things we want to do is we want to go ahead and size this, size that hydraulic cylinder right there. We want to be able to, tell our purchasing guy, okay, go and get one that has, this much force, because that's how much, force we need. Now, in order to do that, one of the things we have to consider, if we go ahead and go into mechanism, applications mechanism, so right here from mechanism, we can go ahead and run a what's it called, a load cell lock analysis. Now, the first thing is within mechanism, you'll notice you have certain ones like position and kinematic analyses. Those are enabled by the base version of mechanism. And then you have other ones that include forces. So, for example, a dynamic analysis, a static or a force balance analysis. All of those are analyses that are enabled by the mechanism dynamics option. Likewise, the functionality for MDO is also included when you see things like, inputting force motors or springs or dampers into the system. Whenever those are activated, you have the MDO option, and you can go ahead and add those entities to your system. In this case, all we're going to do is run an analysis and do a force balance. Now, part of the goal in this case is to say, for example, the way we want this to perform is when it's open 15 degrees, and when it's less than 15 degrees, it should stay closed. But when it's open 15 degrees or more, the hydraulic cylinder should kick in with enough force to push it open all the way. And so 15 degrees is our tipping point. That's our threshold, almost like how the trunk of your car works. And so what we'll do in this case is we'll go ahead and tell Creo, first off, we'll create a load cell lock. And basically what this does is we have to have 0 degrees of freedom in the system, and currently we had 1 degree of freedom, as you saw when I was dragging the model. And so we just had to tell Creo to lock that 3rd degree of freedom, or that last one. And it then gives me this magenta arrow showing me, okay, the value it reports back to me is going to be in that direction, right? And so now whenever I hit run, it runs and says, okay, the reaction force is 0. And you're wondering, okay, nothing happened. It came out as 0. Well, yes and no. And that's because, again, mechanism dynamics can control the influence of forces and also based on gravity as well. And so what we currently have in this case, there's no gravity turned on in the system, and there are no other forces. And so it's just, analyzing this in a weightless environment. And it says, yep, in a weightless environment, you need 0 force to push it up all the way. That makes sense. In this case, we are here on Earth, so we'll enable gravity and rerun that again. And now when it runs, it comes back and says, okay, you need 181 pounds of force in that direction to open it up all the way, right? And so now I'll say okay, and I'll then go ahead and define a force motor pushing against that linear axis that we just optimized. And I'll say a negative 180 for now. Knowing that it told me I need 181, I'm going to ask it for 180 pounds of force at that location and say okay. Now I'll go ahead and create a new dynamic analysis and say, I'll just call this a test. Let's say it's a dynamic analysis, and we're going to enable gravity. Now you'll notice whenever I run this, it starts at 15 degrees and the lid just goes down shut. Because again, it's not above that 181 threshold. Now, what I'll then do is I'll see here, we'll switch back to that open configuration, and I'll edit the definition of my motor here and ask it for, I don't know, 185 pounds of force. And we'll go ahead and do the same thing again. Dynamic analysis, let's run. And now you'll notice what happens. It starts out, notice what happens. It starts out at 15 degrees, and so let's do this one here. Yeah, starts out at 15 degrees, seeing 185 pounds of force from that hydraulic cylinder axis. It pushes the lid all the way up to the open position, which is the performance we want in this case. So this quick example here shows, how you can use MDO to, analyze and query your model for, a certain performance, and then, in this case, accurately size how big of a hydraulic cylinder do we need at that location. Okay. Next model that we have here incorporates a little bit of mechanism, but a lot of behavioral modeling, and particularly in this case, we have what's it called? It's a lot of it is more so behavioral modeling, and so it's actually going to be pretty cool to walk through this. What we have in this case is a reciprocating mechanism that basically forms the basis for your jigsaw. And so whenever you have those, you go to Home Depot and you get a saw that basically has a in and out motion, like that. This is basically, in some cases, the base mechanism for that. And so it takes a rotational input and converts that into a linear output. Well, part of our design requirements whenever we're doing this is to maximize that stroke on the output. So to get that to be as far as we want it to be based on our design constraints. And so one of the things we can do here is just let me run a quick kinematic analysis. Nothing fancy, just runs through one cycle just to show you the motion it's going to go through. Now, in the case of BMX, you can define how Creo targets variables you're interested in by creating many different features and saving them as features in your model. So that way, Creo creates the parameters. So, for example, one of those is a measurement feature. And so I can go right here and say, if I'm interested in that distance, how that moves. Well, I want to get the distance from that face to that face, and I want to make that a feature, and it makes that with a distance of 4. Now, if I go to my parameters section, I can pick on that feature, and now it tells me that feature has a distance parameter with a value of 4 that was measured from those two surfaces. Right? And so now this tells Creo every time you regenerate, pick those two surfaces, measure the distance, and store the value as a parameter. Now I'll then go to the analysis here, and let's see here, we'll run a motion analysis, and we'll pick we'll pick the same analysis we had, and in this case that distance parameter, and we will then run that. Now BMX then goes into the mechanism, runs the mechanism analysis, and receives the data points or the results back from mechanism, and then plots them out like this. Now, one of the things I can then do is I can take a look at this and see, close this here. it then creates certain parameters that I can either, say yes to create or no to not create based on that data point. And so some of those are, for example, um, the minimum value of that distance parameter. So the minimum stroke, I can say, okay, yes, let's create that parameter. Likewise, let's create that for the maximum as well. Okay. Now we know in this particular case that maximizing the value of that stroke or that how far this moves in and out is basically going to be um, well, actually no, it's going to be this right here. So maximizing the value of how far this moves in and out is basically going to be, stroke, and that's going to be equal to the max distance minus the min distance. And we'll go ahead and verify that. And right now you'll notice that value comes out to about 0.9. Okay, and so that's where we are currently at 0.9. So we'll say okay. Now, one of the things we can then do in BMX is to then run some sensitivity analyses to get an idea of what's going on. And so if I say, let's run a sensitivity analysis, I'm interested in the stroke parameter. And the dimension I want you to change is, let's see here, that angle dimension. So the angle dimension for this small cylindrical section right here. Now I want you to start at say 4 and go all the way up to 14 degrees and do that 5 times. And so now Creo then takes 5 even divisions between 4 and 14 degrees and then changes that dimension, reruns the analysis, gets the data value, and comes back in here. And so you'll notice what I just did is the equivalent of running building 5 different prototypes. Only difference is I did that virtually, and it took Creo less than 10 seconds to do compared to if I had to manually do all of that. And so you can imagine how much time you're saving by just defining this and automating it in Creo to have it run. Okay, so now we notice in this case that changing that angle dimension has a fairly significant impact on how much it increases my stroke parameter. Now, to take it a step further, I can then say, okay, well, let's run a feasibility study on this, and our goal in this case is to say, okay, currently we're designing for a stroke value of 1.05. And so we'll set it to 1.05. And I'll also then go here and set my run convergence to, what's it called? 0.001, because I want one that's really, really accurate. And so I want to make sure it really converges. And then we'll add that dimension to it. So that value, and we'll say go anywhere from 4 in this case to 16. Now we'll tell it to compute, and now Creo starts optimizing. It's now looking for a feasible solution. That has my stroke value at 1.05. Now it comes back and tells me, okay, a feasible solution has been found, and whenever I say close in this case, now it pulls out this box, which basically tells you that while it ran the analysis, it changed the dimensions in the model to reflect the best value. And so if you want to hit confirm, it'll keep that value in the model as is. And if you hit reset, it'll reset it back to the initial value you had. And so right now, if I go ahead and I take a look at my parameter now, go so here, yeah, now my stroke value is exactly 1.05. Now, So we did that. We hit that design threshold of 1.05, but we can also go a step further. Not only can we do that, in this case, I want to remove any constraints. I want to say, let's optimize this. Give me the highest possible value you can get for my stroke dimension, and I'm not going to give you any constraints. And so in this case, this isn't where we're just limited by what we want. In this case, we're asking Creo, okay, get me the best thing you can find about that value for the stroke analysis. So what's the best dimension for angle that results in the best value for the stroke? And now when I compute this, it's not trying to meet a particular goal, but it keeps going until it converges at the best design. And now what I'll notice is the best stroke analysis variables is actually one that is slightly above 1.3 instead of 1.05 like I previously suggested. And so you'll notice what it just did in this case. It opened my eyes to see that there's a much better design than what I was initially going for. I could change that angle variable a little bit more and get to a performance of a little over 1.3 for my stroke length. Okay. Now another example that we can go through is one of a hand pump, and I'll switch to that here in a second. Hand pump. Okay. Okay. Now in this case, what we have is a simple case of a hand pump. So you pull on the handle, and it traverses a certain amount of volume inside of that green tube. And in this particular case, all of the parameters and everything has been defined for us already. Basically, we have everything defined to check for example, the clearance between that plate right there and that green tube. We want to make sure they don't bump into each other or interfere. We have things to calculate the internal volume that that piston traverses as it moves into the in and out of that tube, and we want to maximize that internal volume as much as possible, right? And so in this case, we won't go over the mechanism dynamics pieces much. Rather, we're going to go straight into the behavioral modeling, because everything in mechanism dynamics has been done for us. All we're going to do here is go straight into BMX and then tell it we want to run an optimization. And what we want to do is we want to maximize as much as possible the internal volume of that pump. Now, as I guess you could say, way to constrain it, one of the things we want to say is, we don't want that component bumping into the green tube, and so we're going to take that clearance value and say it has to be greater than or equal to 0.25. Anything less than that, and it's too close for comfort. Next is we're then going to give it some variables to change or manipulate as it heads for that goal. And so we'll give it a few dimensions here. First, we'll say this one. So basically the length of this link right here. And then we'll tell it can change the length of the handle itself. And then finally, we'll also give it the position of that link, that hole where the link is. We'll give it the linear position of that until it can change any of those three values. And you can also then define the boundaries or the limits within which it can change those values. So I'll say 6 to 10, and that's going to be from 5 to 10. Okay. Now, based on these min and max values, we can then tell Creo to go ahead and compute. Now, it's going to go ahead and try many different things. It's going to go ahead and okay, I'm going to start here, and then I'm going to change those variables, increase the performance, and it's going to keep going until it gets the best possible performance for this design. Okay. Great. So we just let it, go for a little bit there, and you'll notice, in less than a minute, Creo came back and said, okay, I found the best design for you. It took me 10 tries, but in getting to that design, I was able to increase your volume, the internal volume by, almost a factor of two. It basically went from, just right above 25 to right above 50. Um, and so you can very quickly see how, in this case, BMX saves you time, and also dramatically improves your product performance, because now I almost doubled that internal volume, what's it called, area, just by, you know, tweaking some variables in here. And now, likewise, I'll go ahead and, if I hit close right here, I'll say confirm. And now it, saves the actual, the best possible values of all those different dimensions in the system. And so, for example, if I go ahead and hit edit in this one, that dimension was initially 7, now it's 9.39, because that's the best possible dimension for that hole. Um, Now, finally, we're going to come on here and talk about a chair grip. Um, Now, this is, and I think I had a picture of that on my slides earlier. So this is, what's it called? Whenever you think about a ski lift, and so basically you have all those different, like a rope system with a cable car that's attached to it at the bottom, gripping onto the rope, and then, the rope or pulley basically traverses a certain distance, and the entire, car moves. Well, in this particular case, what we're interested in is the clamping force at this location here. So how hard does this mechanism hold onto the rope, right? And we want to be wary of two things. Number one, we don't want to hold that rope too strong to where we cause the rope ends to fray because of the excessive force and then break, because then yeah, everything's going to fail. But likewise, we don't want to hold it with too little force to where we're not holding onto it strong enough for gravity to overcome the clamping force, and then everything falls down as well. And so we don't want to hold it too little, but we don't want to hold it too much either. Now we'll go ahead and switch to mechanism here. And this particular application contains, a fair bit of MDO and also BMX as well. And so basically what we have here is the entire mechanism already defined with some dampers, basically these blue cylinders, and also springs as well in the system. Now, based on these values, we can then go ahead and say run a quick dynamic analysis. And that then just goes through the typical motion that the model will go through. And one of the things you'll quickly see, if I, right when you start, that's the open position at time equals 0. And then as everything moves, that clamp basically comes down and holds onto the rope, right? Now, not only does it do that, but we can also then calculate a specific value for that. So in this particular case, the reaction force is this value that says CAM1. It's the reaction force at this location right here where it's holding onto the rope. And currently that is about, a little under 4,000 newtons of force. And so it's currently holding onto that rope with about 4,000 newtons of force. Now, So we've been able to get an understanding of right now the way we have it configured. That's how hard I'm holding on to this. Now, there are a couple different things that, input a force into this system. First off, we have all those different components and their weight. And so gravity, has a force in this case, or inputs a force based on the weight of those components. But not only that, we also have, in this case, we also have components like the damper, and also the springs as well. Now, we've already mentioned that we don't want this thing to be, too strong to where it frays the rope, and we don't want it to be too weak either. And so our engineers determined the optimal gripping force is 2,500 newtons. Right now we're at 3928, and so we're, much higher than we want to be, and we want to, tone it down. Not only that, we want to see, okay, how do we then tone it down? Do we change the damping or do we change the springs, right? And so if we go ahead and check this here, one of the things, so you'll notice one of the things we did is, yeah, so one of the things we did is right here, if I go into the relations box, click on this guy, yeah, so there's the spring stiffness value is equal to a parameter that we created called K. And likewise, the damping coefficient is equal to a parameter that we created called damping as well. And then when we go in to take a look at those parameters, K currently has a value of 10, and the damping currently has a value of 0.5. And so we'll go ahead and run a sensitivity analysis, where instead of picking dimensions, in this case we're picking parameters. We're saying let's do that on the damping first off, and let's go from 0.1 all the way to 1. Let's do that 5 times, and I want you to plot that against this this parameter here, because that tells me my clamping force. And now what happens is BMX goes into mechanism dynamics, runs the analysis, extracts the value, and inputs that back into BMX, and it then repeats that process 5 times as I asked it to, each time getting the output variable and bringing it back. And so again, this is, 5 different design changes where instead of me manually having to click through this, BMX can do it very quickly and easily for me. Good. Now, one of the things I noticed right here is that, again, it tells me here that when you change that damping coefficient, it really does nothing to your maximum clamping force, which makes sense when I take a look at the mechanism and realize that everything stretches to a max eventually. But at least this provides quantitative data to back up, the fact that I don't have to chase down this rabbit. I don't have to consider damping in the maximum clamping force, because damping plays almost no effect in the maximum clamping force. And so this is really beneficial because it at least tells me which of those 2 rabbits I should not chase. Right? Now I'll then change this and go to the to the K value, and you can say let's change that anywhere between 5 and 15, and let's hit compute. Okay. Now the same thing goes on again. It basically goes between Creo parametric and mechanism dynamics. Changing that K value 5 different times, and each time coming back into BMX with the output variable. Now, one of the things you'll see, as it's going through this, is the K value very, very, very much, affects, the clamping force at the end over there. So it has a very significant change on the clamping force. Yeah, that's great. And so now that we know this is our variable of interest that gives us the most bang for our buck, now we're then going to go run. In this case, let's see here. We'll run a feasibility study, because in this case, our design constraint, based on our engineer's knowledge, is our clamping force should be equal to 2,500 newtons. So that's what we know we want to get to, 2,500 newtons, and based on that, we wanted to change the K value, and then we'll go ahead and tell it to compute, and actually in this case it may not achieve the solution because I was too trigger happy and I clicked it too early. So I'll interrupt this. Uh, yeah, what I really wanted to do was increase those limits and give it a much bigger range to work within instead of 9 to 11. And so now we'll go ahead and compute this again. Okay, and so now we'll notice it tells us, I reached a feasible solution. You can hit close here and say confirm. And now it's going to set that parameter to that feasible value. And if I go back in here and I take a look at my parameters, I'll notice now my K is about 7.5. And so what it just told me here is initially you had a K value of 10. You can use a spring that's 25% less stiff than what you initially had and achieve your performance target. And so again, this is a case where I can, go back to my boss with the dollar savings and say, hey, we can buy a cheaper spring and still achieve our performance target of 2,500 newtons of gripping force on that rope. And so basically, I hope all these different examples. The aim is to give you guys a fairly good or broad understanding of behavioral modeling and mechanism dynamics. Each one of those individually in themselves and what they do, but also then how you can combine both of them to optimize your mechanism performance. Now at this point, we'll go ahead and switch to any questions and answers. And so if you have any questions at this point, now is the time to type them up in the questions box as well on your GoToMeeting panel on the right hand side. Now, let's see here. Let's take a look at some of the questions that have come in. Okay, so one of the questions that's here says, how do you model friction? And I assume in a mechanism, that's the question is, how do you model friction, when you're inside of a mechanism? And so what I'll do is I will, let's see here, I'll switch to this, and let's go to this one here. So if that question is asking, how do you model the effect of friction, as I'm pushing, this lid up, and how friction affects, those two cylinders moving against each other? Well, you would do that by two things. First off, when you're defining the mechanism, let's see here. Yeah, pick on the motion axis. When you're defining the mechanism, you can set dynamic properties for that motion axis. So, for example, in this case where two cylinders are sliding, inside of each other, I can set dynamic properties, and this is where I can tell it, if there's gonna be, one component bumping against another one and then pushing away. So if there's gonna be a bounce, I can specify a coefficient of restitution. Or I can enable, friction, and I can specify my, values of, static, kinetic coefficient, and also contact radius. And so this is where you can input those, static and kinetic coefficient values. And then it will say, okay, now that then tells Creo to take that into effect, in that particular motion axis. Now, the second thing that you would then have to do once you input that in there is you would then, in the case of in the case of a dynamic analysis, for example, if I say dynamic analysis, under the external loads right here, I can now check this box to enable all friction. And so what it'll then do is it'll check all the different connections I have in my model, and it'll incorporate the friction values I've defined and apply that friction to the mechanism at those locations. So yeah, that's how you would go about incorporating friction into your mechanism. Other questions or comments? Okay, let's see here. So another quick tip that I usually mention to our customers whenever we talk about this here with especially with behavioral modeling, you'll notice in a lot of those cases I used sensitivity studies where I picked certain dimensions and I had BMX change those dimensions between a particular range. Well, usually BMX cannot flout anything that Creo parametric does. So in other words, what I mean by that is if you have a case where you've defined a particular feature one way, BMX can only regenerate based on how you defined your Creo feature. So if I tell BMX to change a particular dimension from 5 to 10, well, I have to make sure that that feature can regenerate between 5 and 10 without failing regeneration. If it fails regeneration, then Creo sends an unregenerated model to BMX, which it cannot analyze, and then BMX says, I couldn't analyze it for this value, and the reason for that is because it failed regeneration. And so one of the key things you always want to do when you're building your model is either from the start or at the end of it, you want to vary that dimension between the start and the end value of your sensitivity analysis. You want to vary that and confirm that it can regenerate successfully. If it can regenerate successfully in sketcher mode or in the part mode when you have the feature, it will regenerate successfully when behavioral modeling takes command of that dimension. If not, it may end up being an exercise in frustration because you're going to try and change a dimension that can't regenerate well, and then BMX doesn't give you good results. Any other questions or comments? Great. So it looks like the river of questions here is dried up. But again, that's definitely not the end of this here. If you have any other questions or comments about about this webinar, what you want to see, other questions you have about BMX, please put you can send me an email. My email address is the very first one on there. You can shoot me an email with any of your questions, and I'll go ahead and answer that to the best of my abilities. And also, if it comes to sales information, you're looking to, can I get a quote for any of these? Because this one looks pretty promising, and it looks like we can get a lot of value out of that. Steve Seymour is our director of sales, and you can shoot him an email, and he'll be able to get you the most up to date pricing on things. At this point, without any further questions, I'm going to end the webinar here. Thank you so much for watching. We really do appreciate it, and we appreciate any feedback you have as well. Thank you.